Okay, in this chapter, simply is one more types of integral. We call it infinite intervals. If type 1, that is the type 1, this is improper integral. So if a definite integral, which is we're given the upper bound, lower bound, right? In general, let me remind you about the definition of integral. So here, an integration, there is a sign here, symbol, stand for sum. And the integrand fx here, small f, dx here. Dx here imply that we're taking the integral with respect to the variable x. And the result of this will be the antiderivative of the integrand fx evaluate from the lower limit to the upper limit here. A definite integral will give us the area of the curve under the curve integrand here, fx. It is simply a number. Okay. When I saw that some of you did a mistake here, you find an integral and somehow you put the integral sign like this. This is incorrect because after you taking the integration, we don't have the sum sign here anymore. We don't have this symbol. Or we also don't have the dx at the end here somewhere. Keep in mind that don't write it incorrectly. Okay. Now, if this definite integral where the intervals is from a to b and the function f has an infinite discontinuity in this interval from a to b, or the intervals is infinite. Either of the case, we call it improper integral. So, for example, let us take a look at the function y is equal to 1 over x squared. It is, the graph of this function is like this, right? And the right of the line from x is equal to 1. So here. If we take the integral from 1 to the point t, where t is larger than 1, okay, it will give us the area of the curve under the curve here, right? Bounded by the lower limit here, 1 and t here, the x-axis and the curve. Okay, this is a number. And antiderivative of 1 over x squared is negative of 1 over x. Okay, we evaluate from x is equal to 1 to t, or in other words, the area is computed by this. It is 1 minus 1 over t. This area is smaller than 1, right? Because on the left, it is 1 subtract a number, right? So it's smaller than 1. Very good. So if if we take the limit when t, the upper bound here, approaches infinity, t goes to infinity. In mathematical language, we write it limit. When t approaches infinity here, of this area, and this area is equal to this guy, therefore the limit will be replaced by this. And from count one, we know that if t becomes very large, 1 over t will be, yes, very small. 1 subtract by very small numbers here, and that limit will approaches 1. Okay? So we claim that the area of the shade region here will approaches 1 as t approaches infinity. Okay? So in math, we don't have to write a long sentence like that, right? We just try to make it easier by writing in the notation like this. Integral when of x from 1 to infinity of 1 over x squared dx, which is the same as the limit by definition. Limit when t approaches infinity of the integral from x is equal to 1 to t, and finally it is 1. So here are some specific cases. When t is equal to 2, right, the area of this will be 1/2. T is equal to 3, the area will be 2/3. When t is equal to 5, the area is 4/5 here. And when t approaches infinity, the area approaches 1. Okay. This is, we call it the type 1 integral, the improper integral of type 1. So this is nothing else but the integrations of this for any number t larger than a, and provided that the limit exists. It means that this result, it will be a constant, okay? Or it does not goes to infinity. In the mathematics, in notation, we can write it this way, mathematical. Or if t is the lower limit, then t is smaller than b, suppose. Then the integration from negative infinity to b of fx dx will be defined as limit of t when t approaches negative infinity. Of the integral from t to b of fx dx. Okay, this definition. So this improper integrals is called convergent. If the limit exists, it means this limit exists, and it is called divergent if the limit does not exist. Or the limit does not exist means when we take the limit, it will goes to infinity or negative infinity. Okay, review this in part 1 if you don't remember. So if the integral from a to infinity and the integral from negative infinity to a are convergent, remember, if it converges, then we can write the integral from negative infinity to infinity is a sum of these two parts. This is a properties of integral, right? If it does not converge, then we cannot write it this way. Okay? Because if one of these does not converge, for example, this guy, if it does not converge, then this will go to infinity, right? Then sum of this and this will be somehow infinity, and we cannot compare these to infinity's terms. Okay, that's it. Well, go through as many definitions. So we can imagine that, okay, the improper integral from a to infinity of fx dx here is the area under the curve from a to infinity here, this curve, okay? Now let us compute this example. Okay, now, because the limit is going to infinity from definition, this is the type 1 improper integral, type 1, right? Observation. Because of this guy. Therefore, this is type 1, then from definition, we know that we can write this integral in limit terms. This is limit when t approaches what? Yes, infinity of the integral from what is it? Very good. From 1 to t. Okay? Remember? So, in order to do this, let us compute the things here first and take the limit later. Okay? Then this integral is not very difficult. And what is it? Very good. It is the natural log absolute value of x when x is equal to n. Very good. So, therefore, it will be limit when t approaches infinity. What is it? Very good. Natural log of t minus natural log of 1. And what is natural log of 1? Yeah, simply 0. Be careful. Therefore, this guy will be natural log of absolute value of t. And what is it? Yeah, it is infinity. Do you remember this? Right? Remember, natural log of a of x base a will be y. This implies that x will be a to the y. Okay? And natural log here of x, by definition, it is nothing else but log base e of x. Okay. Now, take a look at this. Natural log of t. Suppose this is m, right? We don't know what it is, but suppose this is m. Then what does it mean? E to the m, right? If t here goes to infinity, then m should also goes to infinity to make sense, right? So if you don't remember the natural log function and stuff, review it. You can go to the math website, 1021, watch the videos about the exponential functions and natural log stuff, formula. Okay. Do you know where to find it? Okay. Here, math 1021. Go to this LSU. You see these videos. And in these videos, you will see the names of these. It will be 5.1a, 5.2, and 5.3, 5.4. So review these, okay? Not that much. Okay, very good. Then that's it. So here, this limit here, this integral, improper integral, goes to infinity. So by definition, we say that it is divergent. Okay. Very good. This integral diverges or it is divergent. That's it. Okay. Do you have any question up to this point? Is it clear, the idea? Very well. So here, let us take a look at the two cases here. The first example, the integrand is 1 over x squared. The limit is the same, from 1 to infinity. And in this first, in the example, the integrand is 1 over x. And this on the same limit, from 1 to infinity. On the left, this guy converges, but on the right, this guy diverges. Interesting, right? The shape of these two graphs are similar. They're like this. Right? But the rate of this graph, it converges, it goes to 0 faster than the right-hand side. So that is one way to explain why one converge and the other diverge. Okay? Try to think about this. And now you can summarize in general. If P here, the power of the denominator, is larger than 1, strictly larger than 1, then it converges. Or it diverges when P is smaller or equal to 1. So it converges because this integral is converged to 1, right? A specific number. 1 is not, which is not small which is not goes to infinity, converge to a specific number. And the right-hand side, this integral will goes to infinity, right? And by definition, so if an improper integral converges to a number, then we call it converge. And it keeps getting bigger, bigger, we call it diverge. That's it. Thank you for your question. Very good. Anything else? Okay, let us move on. And so we study when the limit is very large, right? Goes to infinity, that is type 1. And the type 2, improper integral, if the integrand fx here, it has some discontinuous point. For example, take a look at this graph. This is the graph of y is equal to 1 over square root of x minus 2. Here, at x is when x come close to 2, right? The difference between x and 2 will be very small, yeah. It is undefined at x is equal to 2 because we don't know what 1 over 0 is. So it's undefined, okay? But if it's larger than 2, it means that it is at 2 plus, for example, on the right side of 2, then this guy will be very, very small. 1 divided by a very small number, it will be infinity, right? And this, we call it indefinite discontinuity. At this point, it blows up here, go very high. So in this case, we call it improper integral type 2. Just a definition, okay? And here, if f is continuous, very important, on this open interval, not very open, but from a strict larger or equal to a to b, and it is discontinuous at b, then this guy is the improper integral type 2. So if this limit exists, it means that it does not go to infinity. Just definition. Similarly, if the function fx here is discontinuous, it blows up or down, go to very large number at a, or small numbers, negative or plus infinity, and this limit exists, then we call it improper integral type 2. Then it is called convergent if the limits exist, and it is called divergent if the limit does not exist or the limit goes to infinity or negative infinity. Okay? And similarly, if this continuous point C is between A and B, and both improper integral type 2 here exist, which means it is convergent, then we can write this integral as a sum of these two things. The idea is that this. If this is the x-axis, y-axis, this is the x-axis here, right? And the graph of the function, for example, it is like this. goes to infinity and then decrease like this. This is A, this is B. Suppose this is the point C where it is discontinuous, right? Then suppose the limit, the area of this converge, or is not a good one. Yes, not a good explanation. Okay, just forget about this because that graph is not good. But anyway, if these two is convergent, then we can write the sum of this will be this. That's it. And I think tomorrow we will start with the example here. Go home and try to do it yourself. Okay? I'll see you tomorrow.